The so between you and drinks, I guess, is something completely different. We have, as in the broadcast industry, have a lot of experience with delivering programming to special purpose receivers, televisions, and in the past, that is to say, through ATSC 1.0, televisions are generally isolated from the rest of the world. That is to say, when you broadcast something to them, the television consumes it, and that's about it. You could record it or something, but there's not a pathway from the broadcast to the rest of the world. And in 3.0, that changes. We have apps and other things that have the capability to both use and interact with the broadcast information as well as information on the internet. And so we need to take care to be secure with respect to the internet at large, which is a much more unsafe place than a vertical television broadcast environment like we're familiar with. So I'm going to talk about some of the things that we're doing in 3.0 to sort of address that problem. Fundamentally, smart TVs like 3.0 receivers are computing devices that are connected to both the broadcast network and the internet, and that opens pathways or attack surfaces to do things which is quite foreign to a sort of traditional television receiver. For example, these three sub-bullets here, fundamentally what we're doing is we're creating a receiver which is a multi-homed IP device. So it's receiving IP over broadcast, and it's simultaneously on the user's home network inside of their firewall. So the television is effectively a bridge without the user's typical firewall protections like a NAT router or things that might be built into a cable modem or an ISP system, and that can be a little dicey. It's certainly a little scary, I think, if you look at what's possible in terms of bad things happening, and even before we've really gone too far in launching and this sort of service, there's been at least a handful of vulnerabilities sort of demonstrated. In some sense, they might be thought of as a proof of concept. These links aren't live in the presentation here, but the link in the second bullet is a link to a story about how someone managed to finagle the display devices at Union Station here in DC to show several minutes of rather explicit content, shall we say, and this is partly my speculation, by directing those devices to, instead of playing content over this internet path, play content over that internet path. The second link describes a similar sort of thing for a downloaded app experience. And in HBB TV, there was a lot of talk about a year or two ago about what's called a red button attack, which is the red button of the 4 colored buttons on your remote launches an app in that sort of system. And what's described is a way to for an attacker to take over things and cause the television to do actions that the attacker wants it to do rather than what the broadcaster intended to be done. So what we're doing, in part to deal with these sorts of threats, in part, is to provide information to receivers which enables them to tell if the data they're receiving is what a broadcaster, or in the case of apps, both a broadcaster and an official app developer intended it to be. That is, you can tell if somebody has messed with it. This is particularly important for apps, of course, given that what I said earlier about how the television is a computing platform with a path to it without going through a firewall that is capable of doing, pretty much anything an internet-connected computer can do. So to begin with, what you have to do to enable a receiver to tell whether what it received is trustworthy, it was created by someone that you trust, is you have to, is what we're describing is you're using a standard X509 certificate trust chain. And what that amounts to is you have a trusted entity, for example, VeriSign or Komodo or somebody, a certificate authority, who will create these certificates for the industry, and that receivers know anything that's correctly signed through to this root of trust is trustworthy. So the trusted entity, the certificate authority, what they do is they issue certificates that can be used to sign things and then verify them by a receiver only to folks that should get them. And the receivers embed what's called the root certificates in their devices as part of part of the software build or part of the manufacturing. And importantly, I think if what the industry chooses to use in terms of a root is one that's already used for the internet, then very little additional needs to be done for receivers in order to be able to verify the signatures. So how that works, how this works generally is there's an object, so some data that's either an application or signaling or something that you create a hash from, like a SHA-256 hash or something, which condenses the object into a significantly long but not terribly long number, which you embed into the signaling signature certificate, the first certificate on the left, which is signed using the broadcaster certificate, or in some cases the broadcaster certificate and the application author certificate, so that the receiver can verify that what they received, the hash of what they received matches the hash in the certificate, and that the certificate was signed by somebody correctly, which was signed by somebody correctly who we trust. So this is something like, you write a check to the power company and you sign your name on it. The bank, when they get that check, they can verify that your signature matches the signature on your signature card. This may be old. I don't know if banks do that anymore. The other important part we first need to understand about the certificate chains is when a certificate is issued to a broadcaster, by the certificate authority trusts that this is a broadcaster and sort of follow the chain. In the case where, say, that certificate gets compromised somehow, so that somebody other than the broadcaster could sign something using the keys in that signing certificate, is we need to have a way to say, okay, even though this thing is valid until 2020, it's no longer valid because somebody walked off with a disk, and we need to be able to do that using offline mechanisms. So originally, or sort of traditionally with certificates, you check that they're revoked by consulting a certificate revocation list, which is sort of a list of here's the certificates which you shouldn't trust anymore, even though you wouldn't trust them otherwise. And that, I mean, that works fine in certain situations, but it's not the it's difficult to manage, and the industry is sort of the web industry that uses this stuff has sort of moved on to what's called OCSP, which is both a way to verify that a certificate is still valid by consulting a server on the internet along the lines of, hey, I've got this certificate, is it still okay, and getting an answer, which is okay in some cases, again, like in a web browser for certain cases, or maybe originally, but it amounts to a fair bit of load on servers. You can imagine that if you're broadcasting an app in a market with maybe 1 million homes tuned to it, at that moment or so, you're going to have about 1 million or more hits on the OCSP server, which is difficult to scale for. The solution is to do what's called OCSP stapling, which is to take that response, which is a sort of a different signed message essentially, and carry it along with the certificates. And so what we end up with is a chain of trust where you have a way to verify that the certificate, which contains the hash of the message, is correctly signed using certificates which are still valid, which is to say they're neither expired nor revoked. And with that building block, that is, you can take a message and calculate whether you should trust this data or not, we can build the security around this. The way that works for things like apps is, because we use the same mechanism, as a similar mechanism as we use for email and signing email with attachments and stuff. You see on the right the multi-part MIME sort of email message structure. What it does is it uses some text tags to separate the portions of your email into pieces, and that's how you send attachments and stuff in email. Is because we're using that mechanism to send apps and other things with the different files sort of all wrapped together in one package, is we use the email mechanisms for securing that, which is called SMIME. And so what we do to include the signing information in the multi-part MIME package is to include the certificates that you need except the root, because the root is built into the device, and the OCSP responses, which give information that the certificates were valid at the time the signature was made. You wrap it all together, and you have a single package that's a signed multi-part message, which a receiver can verify has been unaltered and was signed by somebody who is trusted by somebody that you trust at the time that it was signed. Now, so that works fine. That sort of describes how you do it when there's only one signator on something, only one person you got to trust, which is to say, the broadcaster is sending a signaling message or signaling information, which is things like, where's the content and what's the language of the captions and things like that. For applications, they're signed twice. First, by a application author, and second by the broadcaster. And what this enables is a situation where a broadcaster can trust that the application it received from its vendor was the application created by its vendor. And then the broadcaster signs it so that a receiver can verify similarly both of those things, that it was unaltered since it was signed by the broadcaster, and that the application is unaltered since it was signed by its application author. So it's kind of two layers of security, or a little bit of belt and suspenders. And of course, for signaling, we only need a belt. Because there's no author to the signaling per se. So in a drawing that looks something like this. Reference the earlier drawing I showed. That the applicate, you take a hash of the application, which is in the broadcaster signature and the author signature, and then you sort of verify the two separate chains, which both end up being sort of rooted in the single root certificate. Some other things that we've done sort of for efficiency's sake is for signaling. Some of the information, the certificates and the OCSP responses don't need to be bundled with each signaling message. Because each sort of the collection of signaling messages from a broadcaster are going to be using the same certificate chain, and so that doesn't need to be broadcast in every signaling message. The only thing that needs to be broadcast with each message is the certificate with its hash, and then the receiver can use the chain that came at an earlier time to verify the signaling message. So that's sort of basically how the structures are built, is sort of the fundamentals of the technology that we've created or we're in the process of creating to enable receivers to verify that what they got was what we sent, and there's not somebody in the middle messing with things, or a rogue employee broadcast, sticking something else in the broadcast or things like that. There are a number of sort of more complicated items that also sort of come up operationally on this. For example, how you deal with the case where you've got to revoke a certificate because it was compromised somehow. What's the sort of operational aspect of switching to the new one and then revoking the old one? You don't want to be in a situation where, because somebody compromised your certificate, none of your stuff is still valid. And of course, these certificates will expire over time, and need to be renewed, and sort of you have the similar sort of situation of having to renew them. And then finally, what's been hanging over us in this effort for some time is the details of who's the certificate authority, where the certs come from, who pays what to whom, and how much does it all cost, and do that in a way that everyone trusts the way the situation, the way the environment is set up, so that receivers. How am I doing on time? Oh, I zipped right through it, didn't I? So there's a bunch of operational aspects to do that. Fundamentally, I think, though, what will happen is whatever system you have that's creating whatever system you have that's creating the signaling messages about what content is where, as a broadcaster, that you load up your cert or your certs into it, and that equipment will do that signing as it goes. And similarly, your mechanism for ingesting the application from whoever authored the application in a more secure process, because the apps are a little more dangerous, that your ingest system includes applying the signature to it before they get broadcast. Fundamentally that's the foundation on the data validation aspect of broadcast signaling and app signing that we're working on and nearing completion, Rich, in S36 for 3.0 work. Any questions?
Any questions?
Oh my goodness.
I have a question. Looking at the cellular environment, drawing from it, there seem to be two issues with this approach. One is in a global economy, there's not a single certificate authority, there's a multiplicity of certificate authorities, and the apps that you pull in a commercial environment tend to draw across this universe. And it's been demonstrated that not all certificate authorities for various purposes are trustworthy. So one issue is how do you constrain that? And the second issue that's been identified in the cellular industry is that the device itself may not implement best practices in terms of how it's supposed to check for certificates, might be sloppy in it, might have some parameters. So how do you ensure that both ends of the equation are constrained?
Yep. So with respect to the first question, there's nothing about the system as we've designed it so far that requires it be a single certificate authority, a single root of trust. It's important that receivers have the root installed, and as a result, it's certainly a lot easier if the chains are rooted in root certs that already, that the manufacturers already trust. There's operational advantages, to us, I think, in there being a small number of cert issuers for this use. And but that's sort of a it's ease for us kind of thing rather than a necessary for the system to work sort of thing. And so I think that my expectation is that we'll certainly start off with one cert issuer, certificate authority, but there's nothing about the system that requires that to be the case. As to the second question, yes, it's true that there's nothing that would require a receiver to verify the signatures. On the one hand, it's it's not what ATSC typically does, make requirements on receivers, and on the other hand, if a receiver wants to be vulnerable, if somebody wants to build an insecure product for some reason, then that's not good, I suppose, in a broad sense. But it's hard to produce. It's hard to require someone to build a good product,
But nonetheless dangerous to distribute. And again, judging from the cellular world, I don't think any cellular handset manufacturer has a design objective to build an insecure device, but in terms of expediency, cost, time to market, it's commonly frequently overlooked.
Yeah. Well, to be sure, security is hard and good security is harder, but this is the mechanism we have to enable the security. Phil.
Yeah, and just following up a little bit on that, you talk about certificate revocation and you talk about expiration. Are they at all treated differently? Because I can certainly envision, a certificate inadvertently being allowed to expire, as opposed to one being revoked for abuse. I kind of equated it to if you let your driver's license expire and get stopped, it's different than if you're driving on a revoked driver's license.
Right.
And I would hate to see my service stop because somebody forgot to renew something. Is there like a potential for a grace period
Well, so this is what I was getting at on the last slide. The sort of the operational aspects of how to deal with expiration and revocation amount to, as you're approaching your revocation, your expiry date, you need to acquire new certs and bring them into your system and have that fully operational before the old ones expire. In the case of revocation, you can't. Things happen a little faster because you can't plan months in advance, right? And so the operational aspects of doing the switchover in the case of a revocation are a little more critical. But to your driver's license, example, DMV sends you a note a while before your license expires. And the analogy in our case is you have both your driver's license and an attestation from the DMV that is a correct license, and when or was correct at a certain time. And what happens with revocation is it's not possible to get the attestation that it's correct today. And if you have one that said it was correct last week, that's nice, but the cop, when he pulls you over, isn't going to trust your license, right? But anyway, I think dealing with the expiration of these things is sort of a annual or biannual process that a broadcaster is going to have to deal with to acquire the new certs, load them into the system, switch to them, and move on. The revocation is the same process that fast forward.
Yeah, I guess I was just looking at it from the standpoint of the oversight, as currently I'm dealing with the fact that all my Microsoft products are now out of license because the IT department sort of missed an email.
Right.
And we're scrambling to get our contract re-signed. So
yeah.
I just see that happening, or potentially happening. It shouldn't shut the operation down.
Yeah. Well, I mean, to be sure that's an issue that needs to be dealt with. I think that it certainly would be better for the environment if we don't miss those emails, and if the devices which do the signing for you start giving you really nasty warnings a month or two or three in advance and things like that. But going back to the other question, it's both possible to build a device that doesn't check the signing at all, and it's possible to build a device that it does check it. And if it fails the certificate checking, then put up a red box. I mean, your browsers do this, right? If you go to the site with an expired certificate or one that doesn't match or something, you get the red address bar or something, and IE makes you click twice to get to it and things like that. We could have the similar sort of situation. I mean, it's up to receiver guys what they do. We could have a similar sort of situation like that where you'll both hear about it real quick because people will start calling you, and you be maybe not completely off the air because it's possible to click through in that. But the downside is you have less security because someone could say, "Oh, these frickin'," and click through into the attacker's content, which is again kind of an operational thing. Oh, there might be one more.
Make it a quick one.
It's new, but it's not so new. I worked for Zenith's cable division nearly 30 years ago. We had cable boxes. It was a lot more primitive than the certificates, but they would have technology in one line where the box had to communicate with the host and download its pay-per-view. And if it could not establish contact with the host, the box locked out, necessitating an angry customer calling the cable company to reauthorize the box. And until this problem was fixed due to massive hardware issues in the cable system in question, I got thrown into this one. But I mean, when you're talking about this, I say, what's old is new again, and that's it.
Yeah, well, I mean, that's true. I think what you're describing is something more like, CA and subscriber management, that rather than the receiver trusting the content that it received. But definitely in a cable sort of environment or a cabled environment like the internet, this is not all that new.
Okay.
Okay. Thank you.
Well, the one that Edgar caught, terrific. Thank you.